Hello, everybody. I hope you all enjoyed the break. Can someone confirm, please, that they can hear me? Thank you. So I have a few announcements to make. First of all, if your Penn State user ID starts with the two letters CC through DJ, you're on the hook today to ask a question in the chat so that you get some extra credit. In addition, there's an optional Mastering Physics-based extra credit assignment that's available as of today. It's going to be graded like a normal homework assignment, worth up to half percentage point of extra credit on the course grade. And it's due just before midnight on a week from today. At the same time, the SRTEs are available starting yesterday for 2 weeks. And the reason those two are mentioned together is that credit will only be given for the Mastering Physics-based extra credit assignment, provided at least 3/4 of the students in Physics 214 fill out the SRTE for the course before the end of the SRTE period, December 13th. Also, as I mentioned in an announcement on Canvas, the homework 6, which normally would have been due yesterday or last night, is going to be due tonight instead, 24 hours later than usual, to take into account both the holiday break and also that I'm going to be covering some of the material on homework in today's class. Homework 7 is going to be due a week from yesterday, and homework 8 will be a much shorter assignment. Will be due the last day of class on December 11th. I will also announce some extra office hours for finals week. Those will be posted to Canvas, so please watch there. This coming Thursday, there's quiz 3. That'll consist of 9 questions. The details of what material is being covered and so on is on Canvas. The final exam will be approximately 18 questions. Roughly 1/3 will be from new material that we'll start covering later on today and also for the next few course meetings, class meetings. And then the remainder will be from material earlier in the course. So it's a comprehensive final in that sense. And the final will be split into 2 roughly 40-minute sections with about 10 to 15 minutes between each of those 2 sections. There are some optional Mastering Physics practice questions that you can use for both quiz 3 coming up on Thursday and also for the final exam. And a sample quiz has been posted, and a sample final exam will be posted as well. So today we are going to cover describing particles with waves, which is something we almost got to last time. And that'll lead us to the uncertainty principle for waves, which will then apply to particles. And finally, we'll talk about probability and probability waves. So the classical wave equation is given by this expression, which has a second derivative with respect to space and a second derivative with respect to time. And it works for example, the electric field in an electromagnetic wave. So y, the variable y, could be the electric field E. And the solutions to this equation are just the familiar traveling waves. They have this form. They depend on position and time, and they can be a cosine or a sine function of some difference between or sum of a function of the position and the time. So this describes a wave that's distributed evenly and uniformly all along the x-axis. But if we want to use this kind of formalism to describe particles, then we're going to need something that's more localized, because particles, of course, are, you know, the electron is considered a point particle, for example. So we need to figure out, if we're going to describe particles with wave-like formalism, then we're going to need a way to get waves to be more localized. if you take a bunch of waves and add them together, you can get a more localized wave called a wave packet. And the first example of this that we've seen is when we added just two waves together, where those two waves had slightly different frequencies. And if you add together those two traveling wave expressions with two different frequencies, what we found is that we got a wave that had an underlying frequency that was the average of the two frequencies, and this envelope around it that corresponded to or had a frequency that was equal to the difference of the two frequencies. And this was a phenomena called beats. So if you have two different sound sources that are slightly different in frequency, but otherwise identical, and you have them emit sound waves at the same time, what you'll hear is the average of those two sound wave frequencies modulated by this beat frequency. So it gets basically louder and then softer with time as a function of the difference between the two frequencies. So one of these beats, could be considered a wave packet. Now it's important to note that because the beat frequency here is equal to the difference in the two frequencies of the two sources, and that the relevant time here, or the period of the beats, is equal to 1 over the beat frequency, or 1 over delta F, then we can write that the product of delta T times delta F is equal to 1. So this is sort of a general expression that applies to sinusoidal waves, traveling waves. And because we are going to successfully describe particles with waves, we'll be able to use this same expression and show that it's related to the uncertainty principle for particles. So here it tells us that if there's some spread in time, then the spread in frequency needs to be correspondingly smaller or larger, such that the product of the two is equal to 1. So what if we add, instead of 2 waves to get beats, we add, say, 7. And so that's what's shown here in this figure. Here are 7 different waves that we're adding together. And if you engineer things correctly, what you can get coming out of that is a fairly compact wave packet, basically. It's the sum of those 7 waves giving you something that's got concentrated activity in the center and very little activity sort of in the wings of the resulting function. So this is a smaller and sharper wave packet than what we saw before with beats. But again, we would have this expression holding true. Now I've written it as greater than or equal to 1, which is what you would get if you did a Fourier analysis on more than a small number of waves being added together. So you just have to take my word for it. If you haven't already seen Fourier analysis in one of your math classes, we're just going to assume that this is correct here. So what does this fact that the product delta F delta T equals 1 tell us about the possible time lengths of a wave packet? So what this tells us is that if we construct a short wave packet by adding together lots and lots of different frequencies, so we're going to have a very small delta T then, but in order to make this wave packet, which is so compact, we're going to have used lots and lots of different frequencies, way more than 7. For example, if you put 700 of them together, you would get a very nice compressed localized wave packet. So in that case, the range of frequencies that is used in order to make the wave packet is going to be very wide. So it's going to extend from F plus delta F, or F minus delta F to F plus delta F. where delta F is going to be large. There's lots of different frequencies are going to be used to make it. So we need lots of different frequencies in order to get a very small delta T. Conversely, if we have a large delta T, if the wave function is spread out in time, chances are that's because only a few frequencies are being used. And in the worst case, or in the extreme case, if you had just one frequency used, then it would just be the same frequency over all space from -infinity to +infinity. So it would be completely spread out. And if you only have, a few waves that you can add together for some reason, you're only given a few to play around with, then you might get something that looks like this, where it trails off at either end, but it's still fairly broadly distributed because it's only made up of a few different frequencies. So if it has a few different frequencies making it up, then its frequency composition pretty well, but correspondingly, you don't localize it in time very well. It's spread out in time. Whereas if you have lots of frequencies that are making up the wave function, so you could have a nearly infinite number of frequencies, so you wouldn't be able to count all of them, but then you can get delta T to be very, very small, have the wave function very localized. So let's kind of apply this reasoning that we used just for waves, but instead to particles, because particles, after all, have wave-like properties, right? So we're going to apply this, this expression delta F delta T is greater than or equal to 1 and see what happens. So we're going to take delta T to be the time it takes for the wave packet to pass by one point in space. And maybe it might help to imagine the wave packet looking something like what's shown in the figure over on the right there, moving with some velocity indicated by the bluish green arrow to the right. So during this time delta T, the wave packet moves a distance delta x, which is given by its velocity times delta T. And we can rewrite the velocity as the momentum divided by the mass of the particle. And we can rearrange the terms to get an expression for delta T that looks like that. So it's just the mass divided by the momentum times delta x. So now we need to find the form of delta F, because we have what delta T is in this expression up here at the upper left of the slide. Delta F delta T is greater than or equal to 1. So we have an expression for delta T. Now we need an expression for delta F, so we can plug it into that initial equation. So the frequency itself is generally equal to the velocity over the wavelength. And remember, frequency times wavelength equals velocity. So that gives us this. And then we can rewrite the velocity again as the momentum divided by the mass. And because this is a particle, and we have the de Broglie relationship, we can write, remember that de Broglie tells us that the wavelength is equal to h over p. So we're just plugging in h over p for lambda here. And so we can rewrite this expression as px squared over hm. And now we take sort of the differential of that expression. So we put a delta in front of it, and we get 2px delta px over hm coming out. So there's our expression for delta F. So now we can put this delta F and this delta T into this expression here, delta F delta T is greater than or equal to 1, and see what happens. So doing that, we get this expression here, which tells us that the product of the momentum, delta P, I should say, and delta X, so the product of how well we know the momentum by how well we know the position, is greater than or equal to 1 with this constant, an important constant, out in front. And we can rewrite that by moving that important constant. Remember, this h here is Planck's constant, it equals like 6.6 times 10 to the minus 34. So it's a very small number. So whether there's a 2 here in the denominator or a 2 pi or whatever, either way, it's going to be a very, very small number. And what this tells you is that the product of our sort of knowledge of the momentum, or how much the momentum is spread, times how much the position is spread out, has to be greater than some small number. In this case, written as h over 2. So this is what's known as the Heisenberg uncertainty principle. It basically says that if we know, say, one of these quantities really well, like we know exactly where the particle is, so this delta x is very, very small, then delta p will have to get large in order to satisfy this overall relationship, and vice versa. If we know the momentum very, very well, then we're not going to be able to say where the particle is with a high degree of accuracy. So one important consequence of this uncertainty principle is that a particle that's confined to a finite region can't have zero energy. So let's explore what that actually means. Let's get a little more quantitative and put a particle of mass m into a box of length L. So that means that this delta x that appears in this uncertainty relationship for particles can't be larger than about L. And that means if you just, plug in L for delta x, that delta p is at least roughly sort of h over L. So what we're going to use to describe how well we know the value of a variable, in this case, delta p, we're going to use the standard deviation. And the standard deviation can be defined as the average of the square of the difference between a variable and its average. So this bar overhead, so we have, let me just rewrite this first term here, is the momentum minus the average momentum squared, and then the bar over top says take the average of that. So if you expand out this p minus p bar quantity squared, you get this thing here underneath the overarching bar. Okay, so we have p squared minus 2p times p bar plus p bar squared. And one of the terms, the central term, 2p times p bar, if we put the bar over that, what we'll get is 2 p bar, or 2 p bar squared. And then we can combine these second two terms, yielding this as our expression for delta p squared as a measure of the standard deviation, or as a measure of delta p, defined in this case as its standard deviation. So one question I'd like you to think about is what is p bar? And think about the physical situation we have here. So we have like a box of length L, and there's a particle moving back and forth, inside of this box. And so we make a whole, 1,000 measurements, and sometimes we're going to measure the particle moving to the left and sometimes to the right. And we're going to take all those measurements and we're going to add them up vectorially and take the average. That'll give us p bar for this particle in a box. What will we measure for that p bar if we take a sufficient number of measurements? So please answer the poll. So the momentum can be pointing to the right or to the left, basically with equal probability. We make enough measurements, what will we get for the average momentum? Okay, get your answers in, please. All right, so we're kind of evenly divided between A and C. The correct answer is A. You'll measure an average momentum that is 0 if you have the particle equally likely to be going to the right and to the left, and you make a whole bunch of measurements. You're going to have, n over 2 of your measurements are going to have the particle going to the right, and the other n over 2 to the left, give or take a small difference. And so the average is eventually, if you take an infinite number of measurements, going to be 0. So one important consequence of this, if we, if we plug in that P bar equal to 0 into this expression, then obviously this term here is equal to 0. So it tells us that our standard deviation is just this P squared bar. And P squared bar, we've already indicated, is what our delta P is. So that's roughly H over L quantity squared. And now if we remember that energy and momentum are related, momentum squared over 2m is equal to energy, we can show that the energy must be greater than or equal to some small value, in this case, h squared over 2ml squared. So this is an important result because what it tells us is that if we confine a particle to a small region, it has to have some minimum energy. And that minimum energy is not 0. So this is known a little bit confusingly as the 0-point energy, but maybe the right way to think about it is where you think it's 0, it's actually got some energy. So its lowest ground state energy, this particle that's confined to a small region, is non-zero. It has some small value due to the fact that we're confining it in a small region, and therefore, by the uncertainty principle, which applies because this particle is behaving like a wave, because we're confining it to a small region, there's some uncertainty in its momentum, which translates to an uncertainty in its energy and gives you this minimum average energy that you would expect. So let's apply this. It sounds, it's a little strange to think that you can't sort of quiet something down to have 0 energy by just cooling it or whatever, or not moving near it, or but in fact, quantum mechanics, if we're treating particles like waves, says no, that's not the case. It always has some minimum energy. But let's see what this means in the real world, where we look at sort of a macroscopic object and a microscopic object and compare what these minimum energies are. So the macroscopic object we're going to think about is just this little bead that we imagine on a very thin frictionless wire. And the bead has a mass of equal to a microgram, which is a tiny, tiny mass, but it's, it's macroscopic nonetheless. If you put a microgram bead on your finger, you could probably see it. And this frictionless wire has a length that's 1 micron, which is very, very small. And then we're going to do the same thing, calculate the 0-point energy, but instead for an electron, which is obviously much, much lighter, and it's going to be confined to a one-dimensional box that's roughly the size of an atom, 0.1 nanometers. So in those two cases, what we get is as follows. for the heavier bead on a string, confined to sort of a micron, which is a rather macroscopic length, the 0-point energy is minuscule. It's ridiculously small, 10 to the minus 46 joules. Even if you write it in terms of electron volts, it's still a teeny tiny number. This is basically unmeasurable. It might as well be zero. So in other words, the uncertainty in the energy of a macroscopic particle confined to macroscopic volumes is negligibly small. By contrast, if you take an electron and you confine it to this little box, then what you get is something that's appreciable. So here what I've done, by the way, is I take that expression, E bar equals h squared over 2ml squared, and I've multiplied top and bottom by c squared. I can do that, right? C squared over c squared is 1. And then I have in the denominator this mc squared appearing. That's the rest mass of the electron. And in the numerator, I have this product of h times c and the quantity squared. And this is useful because h times c has been pre-calculated by generations of physicists to be 1240 electron volt nanometers. And this is a conversion constant that's provided on the equation sheet. It's kind of handy to have around. And in the denominator, I can take that mc squared and use the rest mass of the electron in units of electron volts. And then I can leave everything in electron volts and nanometers and not have to convert to, joules and meters, which means you'd have lots of exponential terms floating around. So this just simplifies things. And you can check that the units all cancel out as you would expect. So nanometers squared in the numerator cancels with the one in the denominator. There's an EV in the denominator, and that cancels one of the EVs in the numerator. So you end up with just electron volts coming out, which is what you wanted because this is energy after all. And the value we get is 150 electron volts. So this is still a tiny amount of energy, but of course it's much, much larger than 10 to the minus 27, obviously, by 29 orders of magnitude. But it's also appreciably large compared to, say, the binding energy of an electron in hydrogen, which is roughly 13.5 electron volts. So this is 10 times larger than that. So this is something that if you were confining an electron to this small region, you'd be able to measure it. You'd be able to see that it was confined to such a region and had a 0-point energy as a result, because that 0-point energy would produce measurable consequences. By contrast, of course, again, this little bead on the string having an uncertainty or a 0-point energy of 10 to the minus 27 electron volts, that's completely negligible and is essentially zero. So what this tells us is that quantum mechanics, at least the uncertainty principle part of quantum mechanics, applies to microscopic particles like electrons, protons, and so on, but not to macroscopic particles like this microgram bead, or a baseball or a car or whatever. All right, so we stumbled upon the uncertainty principle when we were talking about getting waves more localized. And so now we've kind of finished our discussion of the uncertainty principle. Let's get back on track and talk again about the wave equation. So recall that's what it looks like. We want now to define a wave equation for a particle. And we're going to use this variable psi, PSI, the Greek letter psi, which is a function of position and time for particle wave functions. So one thing you want to know about particles is where are they? So how will this psi of x and t be related to particle position? So we're going to draw an analogy, and it's kind of a loose one, to an electromagnetic wave. So this wave function up here in the upper right, that quantity y, which is a function of x and t, could be the electric field of a light wave. And the energy per unit volume that's contained in an electromagnetic wave goes as the square of the electric field. That energy is also quantized in units of Planck's constant times the frequency. That's something that Einstein used in order to explain the photoelectric effect. So light we're treating now in this one sentence alone as a wave on the one hand. So the energy per unit volume goes as a square of the amplitude of the electric field, which satisfies a wave equation that looks like this. And the light wave also consists of individual photons that have energy of Planck's constant times F. So what we conclude is that the number of photons that's comprising this light wave will depend on the square of the electric field. So we also remember when we did the two-slit experiment with light waves, the first time we discussed that, we assumed that there were lots and lots of photons, you know, light wave basically continuously shining on these two slits. And then we said, well, what if we dial down the intensity of the light wave so that, you know, basically only one photon at a time is going towards the slits. And then we saw, and I showed you a picture of a screen where each of those photons getting through made a little blip of light that then stayed on the screen, and eventually an interference pattern built up over time. But the photon appearance point was random within, you know, the allowed regions. So what we could say is that the probability that a photon appears at a particular place at a particular time depends on the square of the electric field. Because if the number of photons depends on E squared, then the probability that a photon appears on the screen is going to go as E squared as well. So we're being very sort of qualitative here. By the same reasoning, the same qualitative reasoning, the probability that, say, a particle like an electron is at a certain position, if it's described by a wave function psi of x and t, will be related to the square of that wave function. And I'll just mention as an aside, there's a cute little video here of particles and waves going through two slits and seeing what happens when there isn't and when there is an observer. It takes a few minutes. I recommend taking a look at it when you have some time. Okay, so wave functions give the probability that a particle is at some position. And let's be a little more quantitative now about it. So the probability that a particle is in some range delta x, so now we're just thinking of a particle on the x-axis, is given by the square of the wave function times that delta x, which is just rewritten as the probability density p of x times delta x. In this case, this probability density is a linear probability density. It's basically the probability per unit length. And that's why we have to multiply it by a length in order to get an actual probability. So we can write the probability to find a particle between position x equals a and x equals b, or as shown in this figure down here, between x equals x sub L for left and x sub r for right. It's just the area under the curve of psi of x squared. So that will tell us the probability of finding this particle between x sub L and x sub R. And that sum is written as an integral, shown here, between A and B of psi of x squared dx. Okay, so let me ask you the following question. If we know that this particle exists, so we know there's an electron, and it obeys some wave function. Maybe the wave function looks like this down here, or something else, whatever it looks like. We know the particle exists, so what should the integral, the total probability be between minus infinity and plus infinity along the x-axis? So there's a poll that you can answer for this question. Okay, get your answers in. All right, so most people chose B, which is that the total probability of finding the particle somewhere along the x-axis is equal to 1, and that's the correct answer. And it's sort of a fundamental definition of the probability in this case. The particle has to be somewhere along the x-axis if the particle exists. And therefore, if we add up the probability of finding it at any point along the x-axis, it could be 0.1 over here and 0.1 over there, but all of those probabilities had better add up to 1 because the particle has to be somewhere along the x-axis if it exists, which we posit that it does exist. So this is kind of a fundamental relationship for probability and for the square of the wave function that we're going to use over and over again. It's called the normalization condition. Let's do an example where we apply that. So here's a wave function that describes a particle. It's a bit of a strange wave function. It equals an exponential with a positive exponent when x is negative, and an exponential with a negative exponent when x is positive. So let's sketch what this wave function looks like. So this is psi of x, and here's x. So for positive values of x, it's a negative exponential. So it looks something like that. And for negative values of x, it's a positive exponential, so it's going to look like this. Right here at the origin, or at x equals 0, we reach a peak. How big is that peak? Can anyone tell me? Put it in the chat. That's right. It's equal to this constant c, which is not the speed of light. It's just c. So this value here is c. If we square psi of x squared, if we square psi of x, and write psi of x squared, then we're just going to get something that looks similar, but a bit sharper. And this peak here is going to be at c squared. Okay, so there's some nicer versions of those plots. Okay, and one thing we could ask is, what is this constant c, this normalization constant c? How do we calculate that? What do we do in order to find the normalization constant c? So think about that. Someone said the y-intercept. Well, it's true if you set x equals 0, then you'll get psi of x equal to c, but that doesn't tell you what c is. So right, so we equate the whole area under the graph to 1. So that means that we're going to take the integral over all space of psi of x squared dx and set it equal to 1. Now in this case, psi of x is equal to two different things depending on whether it's positive or negative. But this function has the property, this psi of x has the property that it's symmetric to the left and to the right of 0. So what we can do is evaluate 2 times the integral from 0 to infinity of c e to the minus x over L. And this whole thing is squared dx and set that equal to 1. And if we know what L is, we're given it here, then we can evaluate this integral and solve for c. So that's what I've done here. And you end up with an evaluation here of e to the minus 2x over L between infinity and 0. At infinity, e to the minus infinity is 0. At 0, e to the 0 is 1, so it's trivial to evaluate, don't even need a calculator. And then you can find out, determine that this constant c is just 1 over square root of the quantity L, which has these funny units of inverse square root millimeters, but you can actually calculate what the value is. So we know what c is from asserting that this particle exists, it's described by this wave function, and therefore the integral of the square of this wave function over all space has to equal 1. That requirement, that the summed probability equals 1, dictates what c, this normalization constant, has to be. So now that we have that, we can now calculate the probability as an actual number of this particle being in some region of space. So in particular, we can calculate the probability of finding the particle between -1 and +1 millimeters if it obeys this weird wave function. And that's just, the shaded area here underneath the wave function, squared. So to calculate that is a question of taking this integral from -1 millimeter to +1 millimeter. And again, we're symmetrical about x equals 0. So we can write that as 2 times the integral from 0 to 1 millimeter. And we now know what c is, because we calculated it before. It's over here. It's equal to 1 over the square root of L. So we can now plug in all numbers, basically, and get that the probability of finding the particle in this shaded region here is equal to roughly 63%. So this is kind of the procedure that one follows for converting a wave function into something useful, like a probability of finding a particle somewhere. So for example, we could have a wave function that describes where an electron is radially in a hydrogen atom. And if we want to find the probability of finding that electron between two values of the radius, so at 10 to the minus 9 to 2 10 to the minus 9 meters from the proton, the nucleus, then the first thing we have to do is normalize that wave function so that the integral of the wave function squared from radius equals 0 out to radius equals infinity, in this case, is equal to 1. And that way, when we calculate what the probability is of finding it in some smaller region, we'll get a meaningful quantity out for the probability, just like we got here. So here the wave function was artificial, okay? But the procedure is the same as you would follow in a more complicated realistic case. Namely, you find this normalization constant by forcing the total probability of finding the particle somewhere to be 1. And then using that normalization constant, you can then narrow in on a smaller region to figure out what the probability is of finding the particle there. Okay, so we now know how to manipulate wave functions, and we also know that they give us the probability of finding a particle. You take the square and do the integral over some region. But what's waving? So in electromagnetic waves, the thing that's waving is the electric or the magnetic vector, vector field. For a particle wave, the thing that's waving is the probability. So that psi of x, that is the wave function, when we square it, it's related to the right? So that's the thing that's waving. It's a little weird to think of that, but that's the interpretation that we're going to use. So what's important now is figuring out how we can determine what the wave function might be for a given particle in some physical situation. Because we want to get something out of all this, we need to figure out what the probability is of finding a particle somewhere. That's an important thing to know. Where is the particle and how's it behaving? So what we need is a wave equation for particles, something that will give us what the wave function is so that we can then find the normalization constant and then find the probability of finding the particle somewhere. So to get to that wave equation, we're going to do the following steps. First, remember what the wave equation was for the electric field. It looks something like this, where the electric field, was some traveling wave, dependent on the cosine of the difference or the sum of a function of position and time. So if we plug in basically this E bar into that wave equation, what we get on the left-hand side is minus k squared times E of xt. So I can take this and plug it in here. And on the right-hand side, the second derivative with respect to time will give me a minus omega squared times E. So I can plug that in over here. And if you do that, what you end up with is this expression. Minus k squared equals minus omega squared over c squared. And if you take the square root, you get omega equals k times c. And if you then plug in what we know omega and k are for photons, and I've just written that down here, omega equals E over h bar, and k equals p over h bar. Now I'm using h bars here, whereas before we would use h. So let me just tell you what I'm doing. So omega is E over h bar. This is exactly the same as writing that the frequency equals E over h. So h bar is h over 2 pi, and frequency is omega over 2 pi. So there's just 2 pi factors that have been thrown in there. And in a similar way, k equals p over h bar is related to lambda equals p over h bar. P over h, I'm sorry. Okay. So, where was I? Wait, is that right? Sorry, lambda equals h over p. I wrote that wrong. My apologies. So k is inversely related to lambda. So these two equations are related, which if you remember the relationship between k and lambda, you'll be able to figure out. But anyway, if we plug in these values of omega and k into this expression here, what we get is that E is equal to P times C. So this is getting a little bit messy. I'll be finishing in just a second, so please bear with me. Let me get rid of all this stuff here. So with E equal to P times C, what we have, so the E equals P times C is basically the summary of this equation for an electric field, which describes, if you look at it, an m equals 0 particle. Because if you remember this expression from relativity, the total energy squared is equal to the rest mass energy squared plus P times C quantity squared. And if m is 0, which is what is the case for a photon, this term here goes to 0, and we're left with E equals PC. So in other words, this expression, or this field equation here, wave equation here, up at the top left, top right, describes a massless particle, or a photon. So for massive particles, we need something that's a little bit different. First of all, there needs to be a term in the energy for the kinetic energy and a term for the potential energy. The kinetic energy term has to have the mass in it. If we rewrite this using omega and k, we need something that comes out looking like h bar omega equals h bar squared k squared over 2m plus u. So contrast that to this. We need a wave equation that's going to take us from omega equals kc to this more complicated expression here. If we want functions like cosine omega t minus kx and so on to be a solution to this wave equation, then this new particle wave equation has to have a first derivative in time in order to bring out 1 power of omega, a second derivative in space in order to bring out a square in the k, and it has to involve the potential energy because that appears here too. And we're also going to require that the wave equation is linear in psi of x and t, as that allows waves to interfere. So here's the equation that does that. It was written down by Erwin Schrödinger while he was on a ski vacation in the Austrian Alps. When he should have been skiing, he was writing down possibly the second most famous equation in physics after F equals ma. This is a fundamental equation that describes how massive particles interact as waves. It has a second derivative with respect to x, a first derivative with respect to time, and a term that depends on the potential energy. So we'll explore this in more detail next time. Sorry I kept you late. See you on Thursday. Bye-bye.
Can I ask a quick question, please?
Sure, yeah, go ahead.
Was any of the material that we reviewed today on this upcoming exam on Thursday, or is this all for the final?
Most of this is for the final. The official statement is on Canvas, and that is what I will follow. So I don't want to say for sure, but please look there. I can go look there right now and answer your question.
I can take a look. Thank you so much.
Okay, if you have further questions, please just ask.
Thank you.
Yep. So the additional office hours are probably going to be same as on Monday, only on Thursday. So 2:30 to 3:30 and 5 to 6. I'll set out an announcement later on. There won't be any office hours today. If you have any questions, please post them to Piazza. I'll be looking at Piazza regularly, or send me an email. Okay. Bye-bye, everyone.